Hey everyone, welcome to the last video for this unit where we're going to take a lot of the stuff that we've already learned about our substitution and elimination reactions and put them all together and compare them all four at the same time. So the thing that's kind of neat about these reactions is that all four of them are very closely related. And that's helpful because if we have an understanding of one, then it helps our understanding of another one if we're just learning it for the first time. But this is a double-edged sword because that means it can be difficult to distinguish between these reactions occasionally. So today we're going to just kind of go over an overview of the similarities and differences of all four of these reactions to see what's alike, what is different, and that should help us be able to decide between all four of them when we're not sure which one we're given. And we're going to do a lot of example problems to help practice that. So let's get started with this kind of comparison square chart. I came up with this a few years ago, and it helps my brain sort of compartmentalize this information a little bit. See if you like it. If it works for you, great. If it doesn't work for you, then there may be a different way that you want to sort of create a little summary sheet while you're studying to help you kind of put all the pieces together. So what I've got here is two columns, one for substitution, one for elimination, and I've got two rows for the one or unimolecular reactions and the two for the bimolecular reactions. So if we have substitution and it is a unimolecular process, that is an SN1 reaction. But if we have elimination and that is a unimolecular process, then that is E1. So you can see the one reactions kind of go across on this chart like so. And so will the two reactions. So we can finish filling this in. If we have substitution but it's bimolecular, that's SN2, and elimination that's bimolecular is E2. So this is just what I think is a really visual way to see how they all interrelate to one another, that the eliminations are common because you're eliminating in either case, you end up with similar products, but the one reactions and the two reactions, they go together as well. It's all really interconnected. So let's break this down a little bit more and start talking about how they're similar. So let's first look down kind of our substitution column this way. So what's the same about any substitution reaction? Well, primarily, it's that we think about a nucleophile. And so that's to say we have something that is either neutral or negatively charged, but that it is going to get in there to do a displacement. It's not a base. When we talk about elimination, we're thinking of a base. Here we're thinking of a nucleophile that gets in and it takes the place of our leaving group. So hence the name substitution, the nucleophile is going to substitute out for the leaving group. So for substitution, you not only need a leaving group, but you have to think about where that leaving group is, because based on how substituted a leaving group is, if it's got a lot of carbons around it or not a lot of carbons around it, that's going to kind of determine which field you're playing in, right? SN1 or SN2. Now, in a similar way, let's talk about our eliminations and kind of think about those all together. So in the case of eliminations, we're not thinking about a nucleophile, we're thinking about a base. So something that might have some similar characteristics to nucleophiles, but in this case, they're just there to pull off protons, right? So in the case of sort of the outcome, instead of taking the leaving group's place, the base pulls off that proton and forms an alkene instead. As far as what we need to consider when we talk about eliminations and how to sort of predict products, we want to think about where those beta hydrogens are. See where they're located, which ones are more or less substituted, which ones are more or less available to help us decide how we're going to do this elimination. And now if we think about this from the sort of scope of the one reactions, like I say, or the unimolecular reactions, they have some things in common that are worth noting and reviewing. So let's talk about those now. If we have a unimolecular reaction, that means that we inevitably have a weak nucleophile or base, which means that they're neutrally charged. We also have to go about this in a stepwise mechanism, where in the first step, we have to form a carbocation and look out for rearrangements. Well, you have to rearrange if it will give you a more stable carbocation. Because of the nature of the carbocation intermediates in this reaction, we don't have any stereospecificity for the unimolecular reactions. In fact, it's so not stereospecific that something like SN1 will always give you a mixture of products. We also need to think about not only the stereospecificity, but the regiospecificity, that our one reactions are always going to go to more substituted places because of those carbocations needing to be more substituted to be more stable. So we always want to go for the most substituted regiochemistry that we can possibly get when we're doing a unimolecular reaction. But what about the two reactions or the bimolecular reactions? Well, in those cases, you're always going to be talking about a strong nucleophile or base, which means a negative charge. We have a very different type of mechanism for the two reactions, which is something that we call a concerted mechanism. If you haven't heard me use that term before, it just means that things are happening in concert. And when we talk about it like an orchestra concert, it means that everyone in the orchestra is playing all at the same time. So a concerted mechanism means that all parts of the mechanism are happening at the same time. The nucleophile is coming in as the leaving group is leaving, or our base is pulling off a proton at the same time that the alkene is being formed, at the same time that our leaving group is leaving. So it all happens at once in a concerted fashion. Unlike the one reactions, the two reactions, or the bimolecular reactions, are stereospecific. So that's something that we must pay attention to. In the case of SN2, our nucleophile has to come from behind our leaving group and always gives inversion of configuration. In the case of E2, we can only pull off protons if they are exactly anti to our leaving group. And as far as regiochemistry goes, the two reactions are also regiospecific, but sort of in the opposite direction. Instead of being very substituted, these would prefer to be less substituted. So hopefully this gives you a little bit of a sort of broad strokes overview to see how these reactions are related and kind of intertwined. If you feel like you don't have a good grasp on some of these terms and sort of ideas that we're talking about here, like stereospecificity, regiospecificity, what makes a nucleophile and what makes a base, please go back and watch the other videos again and let me know if you have any questions. But if you're feeling comfortable with these, let's move on to some practice problems. For these first few, let's identify the mechanism by which the reaction occurs. So you don't have to draw the mechanism and you don't have to predict the product, but you have to tell me what the name of the mechanism is that allowed these reactions to happen. So let's analyze, as we've been practicing in our previous videos, thinking about where our leaving group is, what substitution it is, and the strength of our nucleophiles and bases. So all four reactions are in the mix now. It could be any of them. So we'll have to really think critically and carefully because this is the exact sort of problem that I could ask you on the exam. So let's take a look at our starting material and analyze that first. Here we have our leaving group, that OAC. Again, you don't really need to be too worried about the structure. You just need to recognize it as a leaving group. And that is on a secondary carbon. Now that doesn't tell us exactly what we have to do here. Secondary carbons can do either SN1, SN2, or E1 or E2. So really, we still have no ideas. Let's think about our nucleophile. So we have this NH3. Answer the video question, is NH3 a weak or strong nucleophile / base? Neutral nitrogen is a pretty good nucleophile or base, but it's not very strong, so that still fits into our weak category. So we think that we're probably in the one set of reactions because we are having a weak nucleophile or base here, but which are we doing, substitution or elimination? Hopefully you can tell by the fact that we don't have any alkenes in our product that we are doing substitution because this nucleophile nitrogen takes the place of our OAC leaving group. So the mechanism for this one must be SN1. How was that? Hopefully not too bad. Take a second to pause the video here and make a prediction about this reaction. And now let's analyze it. Let's take a peek at where our leaving group is. Again, we have a secondary leaving group kind of on that ring there. So still doesn't really tell us that much. Let's take a look at our nucleophile. Now we have the NaCN, and remembering that anytime we have sodium, potassium, etc., lithium, that's just a singular positive charge. The other piece must be negatively charged, and therefore is going to be a strong nucleophile. If it's a strong nucleophile, we know we're in the 2 reactions category, and then you can think about what's happening in our product. Do we have a alkene or do we do a substitution? And it looks like that CN has ended up here in our product. So this looks like a substitution to me. And because it happened with our strong nucleophile, it had to happen in a bimolecular one-step concerted mechanism. So this had to happen by SN2. Did you get it right? Let's try this last one. So here we have this OTS. That's our leaving group for this question. And yet again, it's secondary, lots of secondary questions. Now let's take a look at our nucleophile or base. We have water. So answer the video question, is water a weak or strong nucleophile / base? Hopefully we'll remember that we've seen water around a lot and it is always doing one of our weaker reactions, either E1 or SN1. But now the other thing to analyze here is we got something at the bottom of this reaction. We have our little hint there that tells us, oh yeah, we're heating this up. And we know that we use heat to favor one specific type of reaction over the other. We know we're in the weak or unimolecular category of the 1 reactions, but with heat, we can favor elimination. We can also tell that that must be the case because of the incorporation of a new alkene in our product. So all in all, this one has to have occurred by an E1 mechanism. Let's try a few more. Pause the video here and make a prediction about this first one. Which mechanism do you think this reaction occurred by? And if you're not sure, let's analyze it. We have bromine as our good leaving group here, and that is a primary carbon. So that probably tells us something about which types of reactions we're not allowed to do. Think for a second, maybe make some notes about what reactions are off the table now that we have a primary leaving group. And while you're thinking about that, let's analyze our nucleophile / base. Here we have the NaN3, right? And we already said that sodium is going to have that positive charge, so that means this N3 or azide has to have a negative charge. So if that's true, then this is a strong nucleophile / base. And looking at our product, we can tell that that N3 gets incorporated, so this must be substitution and not elimination. So all of that considered, we have a strong nucleophile or base. In this case, it's a nucleophile. We have a primary substrate, which means it's easy for our nucleophile to get in there. So that sounds a lot like an SN2 reaction to me. How about this next one? Pause the video here and make a prediction of which mechanism you think this reaction occurred by. And then we'll analyze. If we take a look at where our leaving group starts, we have chlorine as our nice leaving group there. This is a tertiary substrate. So just like the opposite side of our primary substrate coin, think about which reactions are off the table when you have a tertiary substrate. And now we have CH3OH, or methanol, which hopefully you can tell has a neutral charge and therefore is a weak nucleophile or base. So we are in the 1 category of reactions, either SN1 or E1, and based on the incorporation of this CH3O group into our product, I would say that we're looking at a substitution reaction here. We also don't have any hint about heat at the bottom, so this is looking to me just like an SN1 reaction mechanism. All right, let's look at one more. Here we have an iodide and this kind of strange looking nucleophile / base. So go ahead and make a prediction now. Which mechanism do you think is going to occur to have this transformation happen? Let's analyze it and find out. There's our good leaving group iodine on a primary carbon, pretty good. And then if we take a look at this nucleophile, it's a little bit funny looking, isn't it? Because the other ones have sort of just been nice. You could kind of write them out or they were very small to draw, but this is a little bit bigger and weirder, isn't it? But we have to just remember that potassium being there is going to give us a positive charge, and therefore that oxygen is negatively charged. So we have a strong nucleophile or base. Then we have to kind of think about which one of those two it is, and of course you can also consult what's in the structure of our product. But something to remember about this kind of a molecule, is that we have all these big branchy CH3 groups out here. And those are not very good for a nucleophile to have on them because they just make it hard for the nucleophile to get in and attack where it needs to. This, on the other hand, being so bulky, can just kind of get a little bit close enough to pick up one proton, and then it can just go away and not get too close. So the bulkiness of this and the fact that we've created an alkene as our product tells us that we should think about this as an elimination reaction. And because we're in that strong category or that bimolecular category, this has got to be an E2 elimination. Hopefully, it feels pretty good to analyze these reactions, see where we started, what product we made, and get some hints from our nucleophiles and bases to be able to tell what mechanism would have occurred. If you want to get a little bit of extra practice, take all of these reactions that we've identified the mechanism and draw the mechanism out to show how exactly the products are transformed from our reactants. But before you go and do that, let's think about another type of problem that you are incredibly likely to see on our upcoming exam. And that is the PTP, or the predict the products. So predict the products of these following reactions. And we have a few more instructions here. For any reactions that have a star next to them, be very specific with respect to the stereochemical outcome in the products. For any reactions that have multiple possible regiochemical products, you need list only the major product. This last point is often going to apply more so to elimination reactions than substitution reactions, but we want to keep it in mind so that you're not worrying about drawing these 6 million products when I really just need the one. So these ones are going to be a little bit trickier because you aren't given the product. You obviously have to predict it in the case of these reactions. But now that we don't have that piece, we have to really think super hard about which reactions are possible and which ones make the most sense to choose based on the information we've been given. So let's start with this top one. We'll analyze it in the same way that we've been doing before. I like to start with the leaving group, but you start wherever works for you. This is a tertiary chloride leaving group. So we have our good leaving group. It is at a tertiary position, which is kind of crowded, right? So that might mean it would be hard for us to do something like SN2, but let's see if the rest of the information is pointing us in that direction or not. If we take a look at our nucleophile, we've got a couple of carbons and sulfur there. And sulfur can be a little bit weird, hopefully not too intimidating though, because you can just pretend it's an oxygen. If it was an oxygen, we would have ethanol here. And being that there are no alkali metals there, we have to assume that this is a neutral nucleophile and therefore a weak one. So we know we have a tertiary substrate with a good leaving group. We know we have a weak nucleophile, and so that's putting us in the 1 category of reactions. We're either between an SN1 or an E1 mechanism here, and that will help tell us the product. But how will we know for sure which one we want? In this case, we have to look for something that's actually not there, and that's the fact that we don't see a delta down here to tell us that we would be heating this reaction. Because we don't see that, we know we're not trying to favor elimination because heat favors elimination, which means we must be favoring substitution. So this one must be occurring by an SN1 mechanism. If that's the case, let's think about what the product of this reaction would be. First things first, the leaving group would have to leave. And again, I always recommend drawing a quick little cartoon of what your carbocation looks like immediately after your leaving group would leave, and then check yourself for rearrangements. Answer the video question, does this carbocation need to rearrange? Nope, this carbocation is just fine the way it is. It is at a tertiary carbon, right, like we said our leaving group started at, so it's happy right where it is. So with that, then we just need to bring our nucleophile in and do any acid-base steps that are required, and then we would get a product that looks like this. Just like so. The hydrogen on the sulfur is removed in an acid-base step. I'm going to put this structure here in parentheses to say that this reaction is going via that carbocation. You do not have to include the carbocation on the exam. It is just for your own visualization. So make sure your answers on the exam are clear and that whatever answer you want to be your final answer is either placed in the box on the answer sheet or you draw a box around it on your paper to differentiate it from any of your scratch work. This is just scratch work. Okay, Let's move on to the next one. Pause the video here and make a prediction about the outcome of this reaction. Let's analyze it and see what we think is most likely to happen. If we look at where our leaving group is, it's kind of out here on the end of our molecule at this primary carbon. So we have a primary carbon. Think about what types of reactions are not allowed to happen at a primary carbon. And while we're thinking about that, we can also analyze our nucleophile or base. We have NaCN. There's one of our alkali metals, which means that has to have a positive 1 charge, and therefore CN has to have a negative 1 charge. Because of that negative charge, we are in the strong category, or the category of the 2 reactions. So we're either going to do an elimination by E2 or a substitution by SN2. But how will we know which one? We have to think about whether or not our nucleophile or base is better off as a nucleophile or base. It's just the thing that's over the arrow for right now, but we have to give it a little bit more of a specific title. If we think about bases, all of the bases that we've seen for E2 have been, by necessity, pretty big and bulky, because that decreases their ability to be a nucleophile and get in really close to where a leaving group exists. And it increases their ability to just pick off a proton from the very outside of the molecule and do eliminations. Now, if we think about the structure of CN, it's literally only 2 atoms big, so it's quite small. And because of that sort of linear shape, it can get right in there and do substitution reactions without any problem. So CN minus is absolutely going to be more of a nucleophile than it is a base, which means this reaction happens via SN2. And if that happens, then we can just go ahead and predict our product. We don't have to be thinking too carefully about stereochemical outcomes here because we were not told that we would need to know that for this example. And there you have it. There's our product. Let's try this last one. And it looks like we have a star next to our question here, so we are going to have to be very careful with respect to the stereochemical outcomes of this reaction. Now, if we look at what we've been given, we have an iodine here, and that is on a secondary carbon, and it's coming off as a wedge, so we'll have to keep that in mind. So what about our nucleophile? Here, we have an OH group attached to some carbons. There's 3 of them there, and because it is that OH group, we don't see any alkali metals. It's neutrally charged, and therefore it must be a weak nucleophile. And now we can also see a little hint friend down here that we do have heat, in fact, added to our system. So if we have a weak reaction, that's either SN1 or E1, and because we have that little triangle there, we know we're trying to favor elimination, and therefore we are favoring doing this reaction by an E1 mechanism. When we go to do that, think about the carbocation you form as soon as our leaving group leaves. Now answer the video question, does that carbocation need to rearrange? Yes, it absolutely does, doesn't it? We want to put it at a more substituted position, so we would definitely consider trying to go to this position here because that's a tertiary carbon. It's immediately adjacent to where our leaving group left from. After rearranging, our carbocation would then look like this. Now that we have that carbocation rearranged to the most stable position, we can think about where our beta hydrogens are. There's some there, beta to that carbon, and there's some there as well. So how would we know which ones are the most favored? In this case, you definitely want to be thinking about regiochemistry and substitution of the products. But if you go in and you see an alkene at this position would be tri-substituted, as would this one. So since this one does seem to have 2 possible answers that are both just as viable as one another, this isn't the sort of question that I would ask you on the exam, but you could basically make the alkene at either position there. So we could say that we get a 50-50 mixture of both. So we would get a little bit of this product and a little bit of this product. So those are our 2 possible elimination outcomes. So did we have to think very critically about the stereochemistry for this one? Well, not really. That didn't come in at all to me drawing these 2 possible products. And the reason that it is not that big of a deal in this case is because we're inside of this ring structure, and that kind of holds everything in place. When you have a chain, more like these couple of examples that we did before, you have free rotation, and then you need to think about making a cis or trans alkene. So we'll probably run into some more practice like that soon. Let's try a few more. Go ahead and pause the video now and make a prediction for this first product. See what you think the structure would be. Let's go through and analyze this one. Here we have that OTS leaving group, and it's kind of hanging outside of the ring here on a primary carbon. So that tells us a little bit about which reactions we can do and which ones we can't. For instance, that effectively rules out all of our unimolecular reactions because we cannot make primary carbocations. So we have an idea that we're probably in the strong wheelhouse here with our nucleophile or base. Let's just double check that and confirm that here we have that Na, which we know has to have a plus charge, and whatever's next to it, the nitrogen, must have a negative charge. So we definitely do have a strong nucleophile or base. So how do we know which one will happen here? Again, we want to think about those bulky bases that allow us to do the E2 reaction. Because NH2 is really small, again, it's only a couple of atoms big, that means that it doesn't really have that same big, bulky crowdedness to it, and it would be totally fine to just get in there and do substitution. So because of that, we're going to favor doing this reaction by an SN2 mechanism. That means that our nitrogen is just going to go ahead and get in there. And again, feel free to practice drawing these mechanisms if you like. Get in there like so and kick our leaving group out. So there's a couple of quick mechanistic arrows that we can sketch. And now we can predict the actual overall product. Nothing changed about our 5-membered ring there. And we still have this carbon protruding outside of the ring. Be sure to always, always, always count your carbons if you're not sure, because if you're missing a few or adding a few extra, it's going to cost you points. So we can see now that that nitrogen nucleophile came in, and it's still bonded kind of in a similar way to how we started, right? We're bonded to this purple highlighted carbon that is outside of our ring. So there we go. We didn't have to be very specific about stereochemistry there, so that's all we need to write for that one. Let's move on to the next one, shall we? Hopefully these are going well for you so far, and even if they're not, maybe especially if they're not, be sure to pause and try to do these questions yourself before you watch me walk through the answer, because I hope the walkthroughs are helpful, but you won't have me there to do that with you on the exam. So you need to practice taking a guess, even if you really feel unsure and you think you might be wrong. If you make a guess, then hear what went wrong, it'll help you to learn better and avoid those mistakes in the future. So go ahead and pause here and take a guess on this one. Now that you've made your guess, let's walk through it. We find ourselves here with this OAC leaving group, and is attached to this carbon, which has 3 other carbons around it. So that is a tertiary leaving group. That is going to rule out some of our reactions. So things like SN2, we are not allowed to do with tertiary leaving groups. Now we have to analyze our nucleophile or base, and there we see our good friend water. We know water is a weak nucleophile or base at this point. And then we can look at this little hint below here to tell us which one we're going to do, substitution or elimination. We have our little heat triangle there. That means that we are favoring elimination. And with a weak base, we know that that has to be an E1 mechanism. So what's the product? Let's draw out our carbocation just to be sure that we don't need to do any rearrangements. We get to that. Now, answer the video question, does this carbocation need to rearrange? Nope, this carbocation is good as it is. It's already tertiary and everything else is a primary carbon here. So we definitely don't want to mess with that at all. We're going to get our product via this intermediate. And our product is going to be when that water acts as a base and pulls off one of our protons. But which one? How many different beta positions do we have available to us adjacent to this carbocation? Hopefully you can see that they're all 3 methyl groups and they're all 3 identical. So in this case, it doesn't matter which one we choose. Pick your favorite. I'm going to pick maybe this bottom one here and use the beta protons from that position to give me a product that looks like this. So that's one possible way to draw this product. Like I said, all 3 of these carbons are equivalent. So you could easily just as well have drawn this product, which is in fact the exact same molecule, just rotated differently. No matter how you draw it, as long as the structure is correct, you'll get full credit for it. Hopefully that one wasn't too bad. Let's try this next one. This looks a little bit more complicated, doesn't it? And it has a star next to it. So we need to be very specific about the stereochemical outcomes. So go ahead and make a prediction now. And then let's analyze our starting material. We have an OAC and an F. Answer the video question now. Which is a better leaving group, OAC or F? Hopefully this one didn't trick you at all. Fluorine is not a leaving group. It's not even a bad leaving group. It's just not a leaving group at all. Therefore, we have to use the OAC as our leaving group. And that is at a secondary position. So we could be doing any reactions with this so far. We're going to have to look a little bit more on our nucleophile or base to give a few more hints of which direction we want to go in. And if we look over here, we can see that we have that alkali metal sodium there, which means that our oxygen just adjacent to that has a negative charge to it. So this means that we are in the strong category of reactions, either SN2 or E2. And then we have to think about whether this is more like a nucleophile or more like a base. Now, hopefully you're looking at everything that's attached to that negatively charged oxygen and thinking about the kind of big branchy nature or crowded nature of that O. Because it's pretty crowded, that means that it doesn't really want to do substitution. It would much rather act as a base so that it can kind of just pull off one proton and then be done and go about its business. So based on that, in our strong nucleophile category with the sort of extra bulkiness, I predict that we're going to be doing an E2 type reaction here. So let's think carefully about where our beta protons are and make sure that they're in the right position, because for this question, we do have to pay careful attention to stereochemistry. So let's look out for those beta positions adjacent to our leaving group. There's one, there's the other one. So this beta position out here, being right next to that sort of 3-methyl group side chain, doesn't have any protons on it. So we can go ahead and just straight up ignore that because there's no protons there for us to eliminate. What about this other beta position? I sure hope there's a proton there. And it turns out that there is. It's sort of coming out of the front at us. So answer the video question, are we allowed to do an E2 elimination with this as it's written? No, we're not. Now that we have to specifically consider the stereochemistry, we know that E2 reactions must happen via an anti-arrangement of the hydrogen and the leaving group in space. And we don't have that. Right now, the OAC group right here is 180 degrees away from this fluorine. But we can't eliminate fluorines, we can only use hydrogens. So we are going to have to do a little Newman projection drawing and rotation in order to predict the product of this reaction. Luckily, I've got this copy of a pre-drawn Newman here, so we don't have to spend too much time goofing around and drawing a Newman from scratch. Let's go in and fill in some of these things so that we can see how we might need to rotate our Newman, and then we can practice using our Newman predict the product method to figure out what the product of this reaction is. So we'll draw our Newman projection looking from that direction where we have our purple carbon right there in the front that has our leaving group on it. Now that leaving group is kind of coming out of the page at us, so that is going to be here on the right side of our Newman. There's a hydrogen here, that's an alpha hydrogen. So I'm going to label it as such because we don't want to pull that one off. That's not the one that we want. The only other thing that's there is this big branchy group, which is sort of right above our forehead. So that is pointing straight up and in the plane of our page. Now we got to fill the stuff in the back carbon. That's the more important carbon here because that's our beta carbon with a beta hydrogen on it. So if we look down below us, kind of pointing down toward our chin, we have this methyl group here. And then pointing in either direction are our fluorine and our hydrogen. Kind of think of rotating your face and then sticking your arms either up or back, depending on which substituent you're trying to figure out. The hydrogen is kind of pointing out at us, right? So that's on the same side of the Newman as our OAC, so it must end up here. And the fluorine is kind of pointing back behind, right? And that must be right there. So, like I said before, the anti-arrangement here between our leaving group and something else is with that fluorine. That's not what we want for the elimination, so we're going to have to rotate. Let's keep the front carbon consistent and rotate the back carbon such that our hydrogen aligns with the leaving group. In order to do that, I'm going to duplicate our Newman, erase the arrangement of groups in the back, and then fill them back in, having rotated 120 degrees. So our hydrogen went from being at this position, 180 degrees counterclockwise, to that position. That's looking pretty good so far, but let's not forget to fill in all of our other groups just yet. The fluorine was at that anti-position, but it came down this way to sit at the bottom. And our CH3, according to this 120-degree rotation arrow, has to come up and sit here. So now we've done the major legwork here. Let's just scoot these over to give us a little bit more room to help us predict our products. Let's use that Newman predict the products method, where we're going to eliminate our H and our OAC, because those are what's going to get eliminated in our mechanism. And then we have things on either side of our alkene. So we have this kind of 4-carbon group next to that CH3 on the blue side of our alkene, and then we're going to have our alpha hydrogen and the fluorine on the green side of our alkene. So if you're not sure where to start with this predict the products method, always just go ahead and draw in an alkene. And then I'm going to draw in the things that are remaining on our front carbon. So the front carbon is that purple dotted carbon. Let's give that a little highlight here. On that front carbon, we had this big branchy group that's still there, just like so. And attached to that same carbon, right, thinking about which ones are attached to which part of the circle, is our alpha hydrogen on the opposite side here. Okay, now that we've sort of put those in place, you can just align the other groups along the same side as the ones that we decided they match with over here. So that big bulky group is on the same side as our CH3, like so. We'll color code that in a moment. And then the fluorine is remaining on the same side as our alpha hydrogen. So there you have it. Let's move that over a little bit so we can fit in our color coding. These big carbon groups were on the same side, the blue side of our Newman projection, whereas these smaller single atom groups were on the green side of our Newman projection. Now you're not required to do any color coding for your product, but if it helps you, you're welcome to color code it like this and leave it as long as these groups are legible so that I can tell what you've written inside of the circles. Ooh, okay, so that one was a little bit of work. And this is absolutely the sort of thing that I will ask you to do on the exam. There won't be a lot of these because, as you know, Newman projection drawing takes some time. So don't expect an exam full of these, but you should definitely expect to do it at least once. Let's move on to some other ones, shall we? Pause here and make a prediction for this very first reaction. And then let's analyze it. Starting with our starting material, we have a bromide leaving group here at this secondary position. That secondary leaving group doesn't really give us any clues. Pretty much all the reactions are still up for grabs at this point. So let's look at our nucleophile or base. Again, we have an alkali metal cation here, which means that we have to have an anion or negative charge that goes with it. So even though it's sulfur, we're not going to be too concerned by that. We're going to just pretend that it's oxygen. It's kind of like having an OH minus. So in that case, answer the video question, is this a strong or a weak nucleophile? So hopefully that was a pretty easy question. Having that negative charge there is a dead giveaway that this is a strong nucleophile. So if we have a strong nucleophile, we're in the SN2 or E2 categories. How will we choose between those two? We have to look at kind of the size and crowdedness of our nucleophile or base. And in this case, again, it's only a couple of atoms, so it's not really very crowded. It's happy to just get right in there and act as a nucleophile. So this reaction is happening via SN2. And so let's predict what our product will look like at the end of this SN2 reaction. Nothing will have happened to our carbon ring, so we keep that consistent, and our nucleophile SH will have come in at the exact same position where our bromine left. So there's our product. Did you get that one right? Let's move on to this next one. Make a quick prediction to see what you think the outcome of this reaction will be. And now let's analyze our reaction. Starting here with our leaving group, that is on a secondary carbon, which means, again, we can do any reactions. Let's take a look at our nucleophile and conditions and see what hints we can get there. We see methanol again, CH3OH, which is a neutral and an alcohol named functional group. but it doesn't have a charge on there, so that is a weak nucleophile or base. And we got the hint down here to tell us that that's probably going to be acting as a base because we're heating this. So this reaction is going to take place by an E1 mechanism to give us an alkene product. So let's go ahead and think about what our carbocation is, because anytime we're doing a one reaction, we have to form a carbocation. And now let's see if we need to do any rearrangements here. Nope, it's a secondary carbocation, and even though we could get to better carbocations that are something like tertiary, we don't have any tertiary carbons here, so there's no point in rearranging. But now we need to think about which direction will give us the most stable possible alkene. We have to look out for our beta positions. So there's two of them, and they're a little bit different. This one has a couple of carbons, this one is only one carbon. So if we think about the substitutions here, that beta position is primary, this beta prime position is secondary. So answer the video question, which position do we want to remove a proton from? The secondary beta prime position or the primary beta position? Hopefully that question wasn't too confusingly worded. What you want to be guided by all the time is the substitution. In the cases of our eliminations and for unimolecular eliminations, we want to make sure we're always going to the most substituted side. So you want to be picking beta protons that have a higher substitution. Therefore, the secondary is the one that we will favor. So that means we're going to pull a proton off of that secondary carbon and create an alkene right here in the middle of our molecule. Let's try another. Pause the video and make a guess for this one, noting that we have that star there, which means that we have to be very specific when it comes to drawing the stereochemical outcome of this reaction. Now, let's analyze our reaction, shall we? There's our OTS leaving group that is on a secondary carbon. So just like the other two before on this slide, any reaction is up for grabs. If we analyze our nucleophile slash base, we'll see that we find our good friend water here, weak water. We love you, but you're just not that strong of a base or a nucleophile. And then, of course, we have to decide between those two, don't we? And here we don't see any temperature hint. So that tells us that this is at room temperature, or even if it doesn't tell us that, it tells us we're not trying to favor elimination with heat. So if we're not favoring elimination, we must be favoring substitution. So this reaction will proceed by an SN1 mechanism. Now we have to think if we are substituting for an OH group from water at that OTS position, what's the stereochemical outcome if this is an SN1 reaction? Answer the video question. For an SN1 reaction, do we get a mixture of stereoisomers or do we get specific inversion of configuration? Hopefully you remember that we're going through this carbocation intermediate, which again is always helpful to draw. We should check for rearrangements, but there isn't really any reason to rearrange here. We can't get to a more stable carbocation with only one move. And because we're creating a carbocation at all, that means that we have the ability to attack our nucleophile at either side above or below of that p orbital. So that's going to give us always two outcomes when it comes to an SN1 reaction. So one of our outcomes will look like this, where the OH has come in from the top side, the same side that the leaving group happened to have left from. And we will also get the other option where the OH came from the bottom side, which sort of looks like an inversion, but it didn't happen that way specifically. It was just random. So we get a mixture of these two products. Make sure that anytime you have an SN1 reaction, and I've given you this star or a hint to tell me about the specific stereochemical outcomes, that you draw both of these products because they are present in a 50-50 mixture. Hopefully all these PTP questions are giving you a chance to do a lot of practice on predicting our products and also just going through the process of analyzing to decide how you're going to predict which reaction is going to happen, and that'll of course tell you what the product should be. Let's go ahead and do a couple more. And if you haven't been pausing to predict the outcomes of these reactions, please do it for these last three. I promise it'll really help you to get the practice if you put in the time to make the guess yourself. So let's take a look at this first one here. Pause the video now, make that prediction, and then we'll talk about it together. Let's analyze our starting material here. There's our bromine leaving group. It is on a primary carbon, So this is going to rule out our 1 reactions because we can't make primary carbocations. So this has to either be SN2 or E2. And now if we analyze our nucleophile or base, this is, again, it's kind of a funny looking one, isn't it? But we know that lithium has to have a positive charge. So whatever's next to it, the nitrogen, must be negatively charged. And that means that something that we already knew, that we're in the strong set of reactions or the 2 reactions or SN2 or E2. But looking at the rest of the structure of this will help us decide between SN2 and E2, in that it's got some kind of crowded, branchy bits here. Those we don't really like so much, so that is not going to be favorable for a substitution reaction. It means that we're going to want to do instead an elimination reaction, specifically an E2 elimination. So even though we don't have to be very specific about our stereochemistry for this one, we want to think about where our beta positions are so we make sure that we're getting the right product. If we look adjacent to our leaving group here, this is a beta position and there are no others. So that's our only option, meaning that we have to take one of those protons there and it will have to be anti to our leaving group, but we don't have to think as carefully about it because I didn't give you this type of star hint to tell you that we needed to. But one thing you do want to do here is be really careful about counting your carbons. Is that the correct product for this reaction? No, it sure looks right, doesn't it? It looks like we lost the bromine and we made an alkene because we know this is an elimination reaction, but count carefully. This is only a 5-carbon chain with a bromine sitting at the end. And if we count up how many I put in this product, I accidentally included an extra carbon, didn't I? So this is why I tell you to count your carbons and be really careful. Let me draw a chain kind of above these existing numbers to make sure I get the right number of carbons. There's 5. Then that double bond is taking place between the beta carbon, carbon number 4, and carbon number 5. So we get a product that looks like that. Let's try the next one, shall we? Go ahead and pause the video here to make a prediction about the outcome of this reaction and be very sure to be very specific about the stereochemical consequences of whatever mechanism we choose here. For this one, let's go through and analyze. Here's our leaving group. It's on a dash, so we may have to think more about that in a moment, but for now, let's just focus on it being a secondary carbon. That doesn't really give us any big hints because any of our 4 reactions can still happen at a secondary carbon. Let's analyze our base/nucleophile over top of the arrow here. We have another metal cation here, so that has to be positively charged. And here's our N3, which you may remember we've already encountered earlier. That has a negative charge on it. So we know that we are in the strong category of nucleophiles and bases. So just like the one that we did previously, we have to decide whether it's going to be more like a base or more like a nucleophile. We know that, again, it never hurts to compare these to the previous reactions that you've seen. In this previous one, we were in the strong category as well. But that one was kind of branchy and crowded, right? But the N3, that's not got any branches on it. It's only 3 atoms big, so it's pretty small. And that means that we're going to favor to do more of a substitution here and not an elimination. So now we can draw our product knowing that the SN2 reaction happens in a very stereospecific manner where the nucleophile has to come in at the same carbon but in the opposite position in space from where the leaving group is. So it's going to come in at that same carbon, but instead of being a dash, it's going to come in from the top side and be a wedge. So there you have it. That's the product of this reaction. Did you get it right? We've got one more here. Go ahead, pause the video now, and make a prediction about the outcome of this reaction. And now let's analyze this starting material together. There's our chlorine as a leaving group. It is on a tertiary carbon. So because of the tertiary carbon, that's going to rule out the ability for us to do SN2, but 3 of the other reactions are still on the table. Let's analyze our nucleophile or base, and we'll find that that is another neutral alcohol, right? So it's something that looks kind of like water, but it's not actually water. It's got some carbons on it. But its similarity to water is that it is also a weak nucleophile, which means that we're doing one of the 1 reactions, or SN1 or E1. But we can rule out E1 because we don't have any temperature hint here. We're not heating this and trying to favor elimination, so we must just be favoring substitution. So let's go ahead and get ready to substitute this, but as we should do every time with our 1 reactions, we need to draw out our carbocation and see if there's any rearrangements that need to take place. Answer the video question, are there any rearrangements possible for this carbocation? This is a little bit of a tricky question because there's always rearrangements possible. And here we are maybe looking at this carbon adjacent where we have a tertiary substitution. But at the same time, our existing carbocation is already tertiary, so it's pretty stable the way it is, and it's not really worth trying to rearrange at all. So no rearrangement's going to happen here. So let's draw on the product of our substitution, knowing that we don't have to think about that carbocation at all. It's going to stay put exactly where it was. We're going to make a new bond from that carbocation to our oxygen, which maintains its 2 carbons here. Again, being sure to always count if you're even remotely unsure. Even if you are sure, you should still just double check your carbon count. We'll get something that looks like this. Again, the hydrogen here being removed in an acid-base step at the end of our mechanism. So that brings us to the end of our practice problems for today. If any of these didn't really seem to go super well, especially if you noticed that you had trouble predicting one type of reaction. Let's say you struggled to see E2 reactions, or you struggled to predict the right substitution for an SN1 reaction. Go back to those portions of our previous lectures and review the SN1 mechanisms, or review the E2 stereospecificity. Anything that you feel like you were sort of weak on, go back, revisit those areas in the previous lectures to really try to practice up. And then you should definitely feel free to come back to this video, pause it, you don't even have to watch it, but just come back to them, see if you can get it right a second time after you've maybe had a little bit of time to think about it and also reviewed some of the properties of each of these different types of reactions. And of course, if any of these things are not really making sense, especially in the original descriptions of our reactions, please reach out and just let me know. But with that, we have a lot of stuff to review and practice. So again, thinking back about our mechanisms, because there definitely will be mechanisms on this exam. And there's also going to be a lot of these predict the product style questions. That's why we're practicing so many of them today. When you're considering these predict the products questions, you do have to pay attention to regiospecificity and stereospecificity. So make sure that you're feeling comfortable with those types of considerations and also analyzing the reaction conditions like we did here to decide which mechanism you're going by, and therefore that will tell you what the product structure must be. And if all of that is feeling good, well then you can just relax and look ahead to exam 3. We won't have a video in the coming Wednesday because that will be a review day. So you should use that time to practice more, go back through the notes of the videos for anything that doesn't feel super confident or easy for you, and come to office hours or ask me a whole bunch of questions, because that's what I'm here for. So if you have questions on the practice problems that we've done in this video, feel free to leave a comment, post in the discussion forum, come to office hours, or send me an email. But until then, take care.